Welcome to the Deep Dive, where we explore cutting-edge machine learning research and extract the knowledge you need fast.
Glad to be here.
Today, we're tackling a really interesting development in pathfinding, a new algorithm called NWRCA.
That's right, NWRCA star.
If you're curious about how we solve complex problems with limited resources, think robots moving through warehouses, maybe, or even optimizing cloud computing costs, this is one you'll likely want to understand.
Absolutely. At its heart, this paper addresses a fundamental challenge: finding the best path between 2 points when you have restrictions on things like time or energy.
Standard constraints, yeah.
Exactly. But crucially, it also deals with situations where some steps along the way might actually give you back some of those resources or reduce your overall cost.
Okay, that's the negative part.
Precisely. That negative aspect makes solving these problems significantly harder, computationally speaking.
Yeah.
This new algorithm, NWRCA, promises a much, much faster solution compared to what's currently available.
So the core mission of this deep dive is really to get under the hood of this, understand why it matters. We've got the research paper itself, outlining the algorithm and its performance.
Yeah, we'll break down the key ideas.
We'll break down the key ideas, look at how this builds on previous work in the field, and then maybe even speculate a bit on where this could lead us. Sound good?
Sounds great. Let's start with the big picture first, maybe.
Good idea.
The paper dives into the resource-constrained shortest path problem, or RCSP for short.
RCSP.
Imagine you need to get from point A to point B, but you only have a certain amount of time, or maybe fuel.
Like planning a trip with an electric car, worrying about the battery.
Exactly like that. The RCSP is all about finding the route that costs you the least, maybe in distance, maybe money, whatever, while still respecting those limitations. Staying within budget, so to speak.
Okay, that seems straightforward enough, conceptually at least.
Conceptually, yes. But what makes it particularly tricky, and what this paper focuses on, is when certain actions on your path might actually replenish your resources or reduce your cost.
That's where the negative weights come in again.
That's it. Existing algorithms often really struggle with this combination.
Why is that? What makes the negative part so hard?
Well, think about it. If going in a circle could actually reduce your total costs or increase your resources indefinitely.
You could just loop forever and get infinite resources or zero cost. The algorithm might get stuck.
Precisely. Negative cycles. They break many standard shortest path approaches. And even without cycles, negative weights make pruning suboptimal paths much harder. You can't easily say this path is already worse because a future negative step might make it better again.
Okay, that makes sense. So NWRCA steps into this gap.
Right. The paper introduces NWRCA negative weight resource constrained A as a new approach designed specifically to handle these negative weights efficiently, even in very large networks, as long as there are no negative cycles reachable on the way to the goal, that is.
An important caveat.
A very important one. And the authors show some pretty impressive results in their experiments. They claim it can be up to 2 orders of magnitude faster than current state-of-the-art RCSP algorithms.
Wow, okay, 2 orders of magnitude, that's a lot.
It really is. It can be the difference between solving a problem in minutes versus days, or even being able to solve it at all.
So to really appreciate this, maybe we should step back a bit. Where does this problem even come from? Pathfinding's been around a while, hasn't it?
Oh, absolutely. It has a long history in computer science and operations research. You probably know about Dijkstra's algorithm.
Yeah, the classic shortest path, but only for positive costs, right?
Exactly. Finds the absolute shortest path in a network where all steps have a non-negative cost. Then came a search.
Oh, right. That added the heuristic, the educated guess.
That's the one. It uses a heuristic function to estimate the cost from the current point to the goal. This guides the search towards the destination, making it much more efficient than Dijkstra for, large maps or state spaces.
It's like having that slightly psychic guide telling you, hey, the goal is probably over there, so you don't waste time exploring completely the wrong direction.
Perfect analogy. Now, when you throw in resource constraints, things get much more complex.
Because it's not just the shortest path anymore.
Right. Suddenly, it's not just about the distance or cost. It's about whether you have enough resource budget, time, fuel, whatever, to even take that path. A short path might use too much fuel.
So you need algorithms specifically for this.
Exactly. That led to the development of algorithms for the resource-constrained shortest path problem. The paper mentions a few acronyms: RCBDA, WCBA, WCA, NWRCA?
Yeah, I saw those. Alphabet soup.
Huh, yeah.
Eh.
They built upon A and other techniques like dynamic programming or labeling to try and handle these additional limitations efficiently.
And these earlier algorithms, they made progress.
Definitely. Each tackled different aspects or improved performance in certain scenarios. Some focused on just one resource constraint, others tried multiple. But as the authors of this paper point out, many of these existing solutions don't fully or efficiently address the complexities introduced by those negative edge attributes.
The resource regeneration or cost reduction thing.
Yes, that combination of multiple constraints and negative weights is the real killer app here.
It creates this huge search space, I imagine.
It really does. Dealing with negative weights alongside resource constraints can lead to a combinatorial explosion of possibilities. If you're not careful, the algorithm can get stuck exploring just countless paths.
Especially with those negative cycles you mentioned.
Exactly. That's why the paper emphasizes NWRCA is designed for problems without negative cycles on any path from the start to the goal state. It can handle negative edges, just not loops that give you free lunch forever.
Okay, so how does NWRCA actually manage this? How does it navigate this complex landscape more efficiently? Let's get into the mechanics a bit.
All right. So the paper first formalizes the RCSP problem. You have a directed graph points connected by one-way streets, basically.
Nodes and edges.
Nodes and edges, yeah. States and transitions. Each edge, each step you take, has not just one cost, but D+1 attributes. There's the primary cost you want to minimize, and then do different resources you're consuming or maybe gaining.
So cost plus fuel plus time plus maybe something else.
Could be, yeah. And crucially, any of these values, the cost or the resources, can be negative.
Okay.
The goal is to find paths from a start node to a goal node that have the minimum primary cost, while ensuring that the total usage for each of the D resources doesn't exceed its predefined limit, R1, R2, up to R'd.
And you might have multiple paths that are optimal in some sense.
Yeah, exactly. You're looking for the set of non-dominated cost one optimal paths. Non-dominated means there's no other path that's better or equal in all criteria, cost and all resources, and strictly better in at least one.
Okay, so it finds all the best trade-offs.
Essentially, yes. Now, the core innovation in NWRCA involves a clever two-pronged approach, building on the A framework. First, they calculate that heuristic estimate we talked about, HS, for every state S.
The estimate of the cost to get to the goal?
Right. But here's the key difference. They calculate this by performing a backward search from the destination goal node back to all other reachable nodes in the graph.
Huh.
Backwards. Why?
It's quite clever. They run something like a Bellman-Ford algorithm, which can handle negative weights, or Dijkstra with re-expansions, backwards from the goal for each cost component independently.
For the main cost, and then separately for resource 1, resource 2, etc.
Exactly. This gives them a very accurate estimate, HKU, of the minimum cost or resource K needed to get from any node U to the goal. It also naturally detects any negative cycles reachable from the goal during this backward pass. If HKU becomes negative infinity, you've got a problem cycle.
Okay, so this pre-calculation gives NWRCA a really informed sense of direction before it even starts the main search. Precisely. It's not just a rough guess, it's based on the actual path costs calculated backwards. It's like that scout already mapped the terrain from the finish line.
Got it. So that's prong one, a better heuristic via backward search. What's prong two?
Prong 2 is how it manages the search itself, particularly the dominance checking. With these informed heuristics, the main A-like search begins. It keeps an open list of paths to explore, prioritized by their estimated total cost, actual cost so far, plus the heuristic estimate.
Standard A stuff so far.
Pretty much. It repeatedly picks the most promising node X,
Yeah.
lowest estimated primary cost, F1X, from the open list. But then, to avoid getting bogged down exploring too many similar paths to the same node, it uses a sophisticated dominance checking mechanism.
This is where it throws away paths that are clearly worse.
Exactly. Imagine you have two different paths that have arrived at the same node. If one path, let's call it path A, has used less or equal of every single resource compared to path B, and has a lower or equal primary cost, then path B is dominated by path A.
Makes sense. There's no point continuing path B if path A got to the same place better in every way.
Right. Why waste time exploring from B? NWRCA implements this using something called truncated cost vectors. It basically keeps track of the resource usage, but ignores the primary cost for a quick initial check.
Have a quick check first.
Yeah, they have a fast check against the most recently added non-dominated path to that node. If it passes that, it does a more rigorous check against all the known non-dominated paths found so far to reach that node's state, SX.
And how does it keep track of all those non-dominated paths efficiently?
It maintains a list, GTRCLU, for each state, containing the truncated cost vectors of all non-dominated paths found so far that ended at U. When a new path reaches E, it compares its truncated vector TRCX against this list.
Using that dominance rule.
Yes. If the new path is dominated, it's discarded. If the new path dominates some existing paths in the list, those old ones are removed. Then the new path's vector is added. They use a clever data structure trick involving keeping this list sorted lexicographically.
Lexicographically? Like alphabetical order, but for cost vectors.
Sort of, yeah. It allows them to compare these multidimensional cost vectors very quickly to determine dominance. It helps speed up that crucial pruning step significantly.
Wow. Okay. So prong 1 is the accurate backward heuristic, and prong 2 is this really efficient multi-stage dominance checking using truncated vectors and lexicographical ordering.
That's the essence of it. By combining these, NWRCA manages to prune the search space much more effectively than previous methods, especially when negative weights are involved, allowing it to zoom in on the optimal solutions much faster.
And the paper backs this up, theoretically.
Oh, yes. They provide several lemmas and ultimately Theorem 1, proving that NWRCA correctly computes the set of non-dominated cost 1 optimal paths for RCSP problems, provided that no negative cycles exist on paths between the start and goal nodes.
The math checks out.
The math checks out. And then they put it to the test empirically.
Right, the experiments. What do they compare it against?
They compared NWRCA against two recent state-of-the-art algorithms mentioned earlier, RCBDA and URCA. They used a standard benchmark dataset from the 9th DIMAS implementation challenge. These are large, real-world road networks like New York, the Bay Area, Colorado.
So, realistic test cases.
Very realistic. And they didn't just use the standard two costs, like distance and time. They actually extended the maps to include 3 or even 4 cost components to really stress test the algorithms with multiple resource constraints.
Upping the difficulty.
Definitely. They varied the tightness of the resource constraints too, making the problems easier or harder. They ran hundreds of instances for each scenario.
And the results? You mentioned 2 orders of magnitude earlier?
Yeah, the results were pretty striking. NWRCA significantly outperformed both RCBDA and ERCA across the board. It solved many more instances within the 1-hour time limit they set.
Okay.
And for the instances that all algorithms could solve, NWRCA was consistently faster, often by, yes, 1 or even 2 orders of magnitude. We're talking average speedups of 10x to 100x in many cases.
That is genuinely impressive. Was it better everywhere?
Pretty much across all the different maps and numbers of resources tested. The paper mentions it did particularly well on the Florida FLA map, for instance. They even included a figure showing how many problems each algorithm solved over time for one map, and NWRCA just pulls away from the others much faster.
A clear winner in their tests, then.
Based on their empirical analysis, yes, a very clear performance advantage.
Okay, so let's connect this back. We have this faster algorithm, NWRCA, proven correct, handles multiple constraints, handles negative weights carefully. What are the real-world implications? Where does this actually help?
Well, the potential is huge, really. Think back to our electric vehicle example.
The range anxiety problem.
Exactly. An efficient RCSP algorithm that handles negative weights like energy regeneration when going downhill, which is literally negative resource consumption.
Oh, good example.
Could lead to much smarter route planning, maximizing range, minimizing charging stops by intelligently incorporating regeneration opportunities.
So better EV routes. What else?
Logistics and supply chain management. These are massive optimization problems. You might have delivery deadlines, time constraint, vehicle capacities, resource constraint, fuel costs.
And maybe cost savings for certain actions, like backhauling.
Precisely. Returning empty containers might have a negative cost or use fewer resources in some models. NWRCA could enable much more optimized, cost-effective scheduling and routing for fleets of vehicles.
Okay. Transportation and logistics seem like obvious fits. Anywhere else?
Robotics, definitely. Right. Autonomous navigation for drones or ground robots. They often have strict battery limits, resource constraint. Maybe they operate in environments where they can perform tasks that give them a reward, negative cost, or even find charging stations. negative resource use. NWRCA could make their planning much more sophisticated.
So smarter robots navigating complex spaces.
Yeah, and potentially even in areas like network optimization, maybe resource allocation and communication networks, or even some financial modeling scenarios where you have budgets and potential gains or losses associated with different steps.
Basically, anywhere you have a pathfinding or sequencing problem with costs, multiple resource limits, and the possibility of gains or cost reductions along the way.
That's a good summary. The increased speed of NWRCA could allow us to tackle much larger, more complex instances of these problems that were maybe just too computationally expensive to solve optimally before.
It pushes the boundary of what's tractable.
Exactly.
All right, this brings us nicely to our novel notions segment. Building on NWRCA, what kind of future research directions does this open up? What's a cool idea sparked by this paper?
Okay, here's one thought. We talked about finding the best path given fixed resource constraints. But what if the constraints themselves aren't fixed? What if we could use machine learning to help determine the optimal or most useful resource constraints for a given task?
That's interesting. So instead of just telling the EV, you must arrive with at least 20% battery, the system might learn what? Predict the best target battery level.
Something like that. Or maybe predict the ideal trade-off between time and energy for this specific trip, based on historical data, current traffic, weather, maybe even the driver's preferences learned over time.
Okay, how would NWRCA fit in?
Well, because NWRCA is so fast, you could potentially use it to quickly evaluate the consequences of different constraint settings suggested by an ML model. The ML model proposes a few promising budget scenarios, like try arriving in under 2 hours with 15% battery, or try arriving in 2.5 hours with 30% battery. And NWRCA finds the best path for each scenario very quickly.
So the ML guides the setting of the constraints, and NWRCA solves the resulting pathfinding problem efficiently.
Precisely. It could lead to more adaptive user-centric systems. Instead of just a path, the system might suggest both a path and a smart resource usage target.
That's a neat idea. Merging ML prediction with efficient constraint planning. Okay, what's another notion?
Another avenue could be exploring how to combine NWRCA's strengths with reinforcement learning, especially for online planning in dynamic environments.
Online planning, meaning the plan can change as you go.
Exactly. Imagine our robot again. But now the environment is changing. Obstacles appear, maybe new reward opportunities pop up unexpectedly, resource costs fluctuate.
The real world, basically.
Pretty much. Now, NWRCA itself is an offline planner. It assumes the map and costs are known up front. But its speed could make it a really powerful component within an RL agent's decision-making loop.
How so?
The RL agent is trying to learn a policy, what action to take in any given state. To decide the best action, it often needs to simulate or evaluate potential future outcomes. NWRCA could be used by the agent to rapidly calculate the optimal cost to go from potential future states, considering current resource levels and constraints.
So the RL agent uses NWRCA like a fast calculator to look ahead and evaluate options.
Sort of, yes. It can help the agent learn much more complex policies that effectively handle resource constraints and maybe even strategically seek out those negative weight opportunities like grabbing a temporary power-up or completing a bonus task in real time.
It could lead to more intelligent, adaptive agents that don't just follow a plan, but actively optimize their resource use on the fly.
That's the potential, yes.
Yeah.
Creating agents that are not just goal-directed, but also resource-savvy and opportunistic in dynamic situations.
These are fascinating directions. Integrating learning for setting constraints, using it within RL for dynamic adaptation.
Yeah, and it's important to stress, these are just, speculative ideas. There would be significant research challenges in actually making them work robustly.
Of course. But it shows how a foundational improvement like NWRCA can spark new ways of thinking about related problems.
Definitely.
So to wrap up, NWRCA looks like a really significant step forward for the resource-constrained shortest path problem.
Absolutely. Especially its ability to efficiently handle multiple constraints and those tricky negative weights without getting bogged down.
And the empirical results suggest it offers substantial speed-ups over existing methods, opening the door to solving larger, more complex real-world problems.
From EV routing and logistics to robotics and beyond, the potential impact is pretty wide.
If you want to dive deeper into the algorithms, the proofs, the experimental setup, all the technical details, we included a link to the full paper in the description. Definitely worth a read if this area interests you.
Highly recommended.
And with that, we'll leave you with a final thought to mull over. As our world demands more optimization under tighter constraints, energy, time, cost, materials, How will algorithms like NWRCA, which cleverly navigate these complex trade-offs, continue to shape our technology and decision-making in the years to come?
A big question indeed.
Thanks for joining us for this deep dive.